Welcome. I appreciate your time joining us to take a look at this webinar. This is actually being recorded after the live session. I wanted to clean it up and make it a little bit more concise so that you can get done with this in a reasonable amount of time. There were a lot of questions in the live session and it went on and on. All right, anyway, we're going to give a brief overview of industrial cybersecurity in general, and then we'll actually dive into, that will actually set the groundwork, if you will, for why it's so important to be able to quickly determine if your safety functions are vulnerable. And so we'll actually show you how to do that today. So thanks for joining us. Let's get started. So we're not going to actually show you a picture or a video of me today while I'm talking, but this is me. My name is Jim McGlone. I'm a global industrial cybersecurity professional, certified for quite a few years now. I forget how many years, probably about 10 years. I have undergraduate degrees in nuclear physics and computer technology and an MBA in international business. I used to be a nuclear power plant reactor operator on submarines for the United States Navy. Did that for 9 years, was an electronics technician. Graduated before I got out of there and never looked back, quite frankly. Never went back into the nuclear power industry directly. I came out of there, worked for a Rockwell Automation, we used to call them Allen Bradley back then, distributor, back in the late 80s and early 90s, and then Rockwell Automation kind of won the war. But I lived for rebranding, right? So it takes a while when all those acquisitions are done to get the branding right. But Rockwell Automation today, obviously, and a great company. Really enjoyed working for them. I left there and went to Honeywell. Was vice president of a Honeywell business for years, and left there and actually jumped into cybersecurity big time with Ultra Electronics in Washington, D.C., and left that eventually and became a technical consultant and the chief marketing officer of Connexus. And I am the co-author of Security PHA Review, which I suspect is why most of you are watching this, is to figure out how to do a Security PHA Review or a Security HAZOP Review, which is what we're going to actually do today. There's my contact information. You're more than welcome to give me a call. That phone number rings through Microsoft Teams to my cell. And that is my corporate email address. All right, let's get started. So I personally really like it when people tell me, hey, here's what we're going to go over, and then at the end remind me that that's what we went over. It kind of lays the groundwork, if you will, for the content that you're going to see. So the first thing we're going to do is I'm going to describe the problem and make the case for doing, for basically analyzing things about safety functions a little differently than the IT and the cybersecurity people typically would like to do. And I think you'll understand as we go through that. I'll describe what a Security PHA Review is. I'm going to assume, just for expediency reasons, that you know how to do a HAZOP. It's Hazards and Operability Study, and that you understand what a layer protection analysis is, a LOPA. If you don't know those things, you're more than welcome to contact me. I'll walk you through them and explain them to you. You might be watching this for other reasons. You might be a cybersecurity guy watching this wondering what's this all about. I'll gladly share that with you offline. You have my contact information, obviously, from earlier in the presentation. And you'll get it again at the end. I'll actually show you how to perform a Security PHA Review on a HAZOP. All right, and then I'll actually show you a real-world scenario and how a Security PHA Review analyzes it, which I think will be very helpful. And then we'll briefly consider some non-hackable solutions to problems, and then we'll do a little bit of a conclusion slide near the end. All right, so when we do cybersecurity, basically we have this hierarchy, if you will, that we go through, and a little bit of this is defined from, you'll see down there underneath the protect, about halfway down the list on the left-hand side, that talk about the risk management framework that the Department of Defense uses and the National Institute of Standards cybersecurity framework. Those are both fantastic things. There's nothing wrong with them at all, but it basically, in essence, they measure your ability to do the things that are listed here, right? So how do you identify, protect, detect, respond, and recover? And it's interesting. I'm just going to start with the first one under identity or identify, asset identification. You would be surprised how few people have any idea how many controllers, programmable logic controllers, any type of programmable controller. If you're in the building automation space, variable air volume controllers, air handling equipment, how many units are there? You go into manufacturing, how many PLCs are there on the assembly line? How many are there in this cabinet? It's mind-boggling to cybersecurity people, because if you haven't identified your assets, then you really don't know what you're trying to protect. So understanding assets is a complicated problem. It takes effort, but I will say that you should probably have a list of every one of them that can be programmed and verify that they have the right firmware in them, and they have the right version of code running in them, and that you have a backup for that just in case something goes wrong someday. So under identify, we do things like asset identification. Believe it or not, an audit really helps in the identification phase. A vulnerability assessment, it's a very real thing. Penetration testing in the operational technology space, I'm always hesitant to do this. If you have a pen tester that really doesn't know what they're doing, you run the risk that they come up against an older controller or something, and you could actually make it malfunction. And best case, you might just shut it off or make it pause, and in worst case, you might brick the thing. So you got to be careful, and you got to know what you're doing. Understanding vulnerabilities. I'm not going to go through all these. You can read these on your own sometime. Under the idea of protection is mitigation, strategic planning, remediation, commissioning, secure system design. So when somebody's delivering a package unit to you or something like that, is it designed correctly to fit into your system, not just from a process perspective, but from a cybersecurity perspective? Did they do all the right things? Did they set them correctly? Did they set the security functions in the controller? Did they remove the defaults and put in something else, right? Maybe you're going to do that, but you at least need to think that through. Under detect, one of the things that companies seem to really struggle with for some reason, they leave it up to the IT department, is security monitoring, threat intelligence efforts, stuff like that. It's not that hard to do. There are ways to do it. We do it here at Connexus. We actually do security monitoring. I actually run the IT infrastructure. We have software guys who are very good at doing security monitoring too, and we watch the things that we built and the architecture that we have very carefully to make sure that nobody's on it that shouldn't be on it, if you will. We watch ports, Wi-Fi access connections, even failed attempts to connect to see, hey, what's that device that's trying to connect? So we get little warnings, and when you get security monitoring right, you don't see everything. What you look for are the anomalies. So something to think about. Response. This one kills me. Response and recovery. I'm going to combine these two together. So there is a structure to responding, a playbook, if you will, like it says here. And understanding that gets really important. Recovery. I watch the news, and all these people that get attacked by malware and they have no way to recover is insanity to me, quite frankly. If you don't just do something simple like back up everything on a regular basis, then you get what you deserve, to be honest with you, because you're just ignoring the fact that someday something's going to go horribly wrong. And backups are amazing. I've had problems in the past and been able to go to a previous backup. I made a mistake programming our website one time and crashed the website and went, wow, that sucks, and went to yesterday's backup and did a recovery and was operational in about 3 minutes. That's the only time our website was really down. And so, you got to be ready for those things. So, yeah. Anyway, let's talk about how many people it takes to do this. At our company, there's 2 people that are focused on this all the time. So 2 people out of many, but the reality is the 2 of us are very good at this stuff. In a regular company, depending upon the size, if you're running a chemical manufacturing company and you've got, let's say, a dozen sites around the world, and each one of them have 100 employees, and corporate headquarters maybe has 100 employees, this could be a really big task, right? This might actually make up, your cybersecurity team might make up not only a huge part of IT, but a huge part of OT, the operational technology space. You could have a person at every site that's a cybersecurity person that's doing this. This is definitely a full-time job. It's just trying to keep on top of all this is very challenging. So it's tough. And so when somebody says, hey, maybe we should take a look at our operational technology, this is kind of what they're talking about, right? Is that maybe we ought to be doing some of this stuff. So I love cars. I love trucks. I love motorcycles. Deep down inside somewhere, I'm still like a 16-year-old kid, right? Even though I'm 64 years old. My first car was a... Okay, let me say something. I really wanted this 1965 GTO. That's not what I got. I got a 1964 Pontiac Tempest, which was basically the same frame on the same chassis as this. A little bit different headlights and taillights. But it was my grandpa's car, and that was my first car. It had a 326 cubic inch V8 with a 2-speed automatic transmission, bench seats in it, no seat belts. Red vinyl inside, and it was black outside like this one. It was definitely not this car. Believe it or not, I did have those tires and wheels though. But it was, it was a great car. I wish I had it today because people would literally stop in their tracks to see it because it was an awesome automobile. But cars have come a long way. Oh my goodness. This vehicle had a steering wheel that if you had a head-on collision, I'll guarantee you it was going to kill you. Steering wheels today have airbags in them. You don't even hit the steering wheel in a head-on collision. Crumple zones came along long after these cars were built. Power windows, airbags. I had an AM radio and crank windows, more airbags. Oh my goodness, airbags are everywhere. Power locks, drive-by-wire technology made my emergency brake a push button. Backup cameras, lane detection, auto-dimming headlights, remote start, automatic collision avoidance, and now even self-driving cars to a certain extent. In the not too near future, I'm sure we'll have self-driving just about everything. And so this is awesome, right? And so you could assume that if that's happening to automobiles, that's even happening to the manufacturing space, right? I remember the first time I saw a Chevy Chevette being built out in out near Youngstown, Ohio. And I walked in the factory and went, wow, I was a kid, right? I was a young kid. It was a field trip we made. And all I could think was, I never am going to work in manufacturing ever. It was dim. It was dark. People were not, they were working, and so they were dirty and greasy. The entire thing just was not appealing. So manufacturing has come, as far as the cars have come, manufacturing has come too. So the thing about the vehicles getting so much better, and by the way, that's actually what I drive today. So it's a very basic work truck. It's funny because F-150, even stripped down and classified as a work vehicle, still has a lot of cool stuff in it, like Apple CarPlay, air conditioning, cruise control, power windows, power locks, all the cool stuff that you would really want in a vehicle. I just have one that's kind of beefed up like you can see in the image. It's got a heavy-duty suspension, a heavy-duty towing package. It's four-wheel drive. It has all kinds of augmented methods of putting the vehicle into four-wheel drive. You can put it, you can adjust the way the four-wheel drive works for, like, I'm stuck in the mud versus I'm stuck on ice. So the vehicle does some really cool stuff. It has a a camera in the up where the rear view mirror is, basically in the chassis, that points out the front, and it auto dims the headlights. So you just leave the headlights in automatic, and it does everything for you. Even when you're driving down the road, it turns the bright lights on, and if a car's coming, it turns the bright lights down automatically. It's fantastic, right? That's a work truck. So I'm driving around in a work truck, and one of the warnings, it has remote start, so I can turn on my cell phone and tell my vehicle to start as long as I'm within a certain distance of the vehicle. I could make that much further away, right? So I could basically land at the airport and go out over the internet and tell my phone or my truck to start, so it was nice and warm by the time I got there in the parking lot. But the reality is, I sat there and went, do I really need my truck connected to the internet? Let's just think about that for a minute. My cell phone's already connected to the internet. Do I need to connect my truck? And the answer was no. I thought it through and went, I actually don't need to. I have everything I need. It works very well. I don't need a Wi-Fi hotspot rolling around on wheels that somebody could potentially hack. Remember, I'm a cybersecurity guy. I think like that, right? But the question I asked myself is, wow, if I accidentally, I start thinking this stuff through, and I'm like, if I drove into water, would my power windows or power locks fail? Could I unlock my door? Could I put my window down to get out of the vehicle, or did I just create a tomb for myself? What if any collision system hesitates or fails, and I've started to rely on it, right? I drive in and out of Columbus, Ohio, and sometimes the traffic is horrendous. And I've actually not hit the brake fast enough for the vehicle in the past, and the vehicle's like, hey, warning, and it applies the brake for me automatically. Well, if you start to rely on that, and it doesn't actually work right, what happens, right? That car I showed you on the last slide, I'm driving down the road one day and wonder what happens if you turn the ignition off. So I turned the ignition off, and the vehicle just kept rolling down the road, but it, no longer had power applied to it. It didn't have power steering. It had a large steering wheel. So I could still steer the vehicle, and the emergency brake was actually mechanical, so I could still apply the emergency brake and stop the vehicle if my brakes failed. The thing that I actually think about driving these new cars, like when I rent one and I drive it and I'm like, oh my goodness, this thing does even more than my truck. I think to myself, I wonder if I'll be the one that discovers the next need for a recall. It's kind of scary, right? What could go wrong? And so you got to start thinking like this when you're walking around a plant and you're looking up at, some chemical process and saying, wow, if we lost containment here, bad things would happen. And I wonder if we've checked everything to make sure that can't happen. So believe it or not, there are actually people in the world that believe industrial control systems are not vulnerable. I have this conversation on a regular basis with people, and I'm polite. I hear them out, and I understand what they're trying to tell me. They don't want to start implementing the things that IT's already implemented on them, right? So when I worked in the Washington, D.C. area, the cybersecurity requirements for the federal government were insane. You had to have this card to basically put into a computer so that you could log in, and then your password had to be this horrible thing. And it was so large and so insane that you had to write it down somewhere, you couldn't remember it, and then you had to change it every single quarter. Trying to figure out password strategies and come up with something that made sense was very frustrating. And then having somebody come along and say, you got to learn how to use password manager. You got to turn on two-factor authentication everywhere, and on and on and on. And people are like, come on, man. I'm trying to operate a plant. I don't want to do that. However, these operational technologies have been being hacked for a long time. This has been going on for a while. And it has huge ramifications. Not all of these things make the news. As a matter of fact, most of them don't make the news. But the challenge we have is that, the Stuxnet cybersecurity attack, it was named that by the person who discovered it, was a uranium centrifuge plant that was purifying uranium ore, getting it to a higher concentration level, right? And so when uranium comes out of the ground, there's not a lot of it in a chunk of ground, right? Whatever measurement of ground you're going to use. So they spend different ways trying to get it down to a point where they can actually make it fairly pure so they can use it for fuel, let's say, or for other reasons. And this particular facility was buried in a mountain, hidden from the world, wasn't on a map anywhere. No one technically knew it was there. There are some things that happened that, made it easy to hack this thing, believe it or not, even though it was completely air-gapped. There was no wire going in and out, no wireless communications going in or out. They were still able to hack it. So the reality is, with enough motivation, I don't care what you do, people are going to get in. So the bottom line is, you got to be able to recover. The operator stations and the call center for the Ukraine power grid before the war started. Now everything's changed because of the war, but before the war started, there was a huge power outage in Ukraine, and there were a lot of lessons we learned from that. That was a very deliberate attack. It was a very interesting attack from a cybersecurity perspective for us that are practitioners to diagnose and figure out whether we can protect against it. And the reality is we can, but in their case, they had some things on their side. They still had mechanical processes where they could actually put somebody in a truck to go out and turn stuff back on. But the reality is, we learn a lot every time these things happen. And then, chemical manufacturing, refining, basically anybody who's working with delicate processes or dangerous processes in containment or chemicals in containment. Safety instrumented systems, we use those for a reason, right? We use those because they're extremely reliable devices. They've done things to make that thing much more capable of responding to a demand, an input changing or an output changing. They've made those things pretty bulletproof. And then what we do operationally is we leave the bloody remote switch in remote. So we go over it instead of putting it in run because we don't want to be bothered by having to send somebody out to put it in remote mode so you could reprogram it. We leave it in remote, and the reality is that actually caused a hack. And I've seen it in the PLC world, and if you leave your devices in remote mode, you deserve what you get. I'm sorry, that's just the facts, right? So the bottom line is that your industrial control systems, whether you know it or not, are a target. They're a very deliberate target. Governments, like the examples up above, the first two, the Iranian attack and the Ukrainian attack, that was, governments attacking other countries, right? So government cybersecurity people attacking another country. They're trying to learn what your systems are, what access they can get to them, and if they want to throw the switch someday, they can throw the switch. You need to plan for that day, quite frankly. The code you see on the right, so part of the problem here is that we just don't know, right? Not only don't we know where our assets are, we don't actually know what kind of code's running in a lot of this stuff. And you just got to know more. By the way, the code that you do see that's kind of faded out on the right-hand side is actually the Connexus.com website code that I run. So I needed some code snippets, and I went, just go grab some code off the website and stick it up there. I did go through it. It's just graphics code. It doesn't do anything, but it is, you could, if you could figure out how to hack that, you could deface my website. So something to think about, right? And so I have backups just in case somebody does deface my website. I can recover it in a few seconds. And I have the ability to switch my DNS system so that even a denial of service attack will fail very quickly. All right? So things to think about. So this is always an interesting slide. Years and years ago, I worked for Rockwell Automation, and I was very involved in the software development side of the business and building businesses around software and selling software. And I love industrial automation software. It's just, I grew up with it, right? When it was invented, I was there. So this is cool stuff to me. Routable protocols are the same thing. They're awesome, right? Being able to pick your cell phone out of your pocket and route around the world to a website and connect to it and look at information is just phenomenal, right? But the problem is that that Cisco switch you see in the upper right-hand corner is actually an industrial switch. It's a bloody good switch. It's a great industrial switch. you got to have some knowledge to set it up correctly and to protect it, but it's a great switch. And that allows PLCs to communicate very easily to people in other places, and allows the machines to talk to each other, stuff like that, right? So we can have good SCADA systems, good HMIs, good data historians, and we can perfect our processes and make them run better and better. And all of that is fantastic. Don't get me wrong, I'm not an advocate to disconnect it. I am an advocate to understanding it and understanding how to protect it. The other challenge is wireless stuff, right? So you've got a lot of wireless going on. Everything's becoming digital, remotely programmable or configurable. And the device below the Cisco switch is actually a 2-wire Ethernet device. So you see the side where you plug the Cat5 cable in, for instance, and a power connector to that device. But let's flip it around and look at the back of it real quick. At the back of it, it basically runs a twisted pair of wire. Wow. So in essence, what we're going to is you're going to be able to run your sensors on a routable protocol up to that switch, to your PLCs, to your programmable controllers, to your building automation systems, things like that. So that's great, but that also means now that the devices that are out at the edge could be spoofed. So things to think about. Very challenging. So why is this important? So what? Well, this is kind of the ISA 62443 model for how we lay out factories. So we have down at the bottom, the yellow box is the basic control layer. So this is where PLCs go, programmable controllers, whatever you call them, right? I'm going to call them PLCs because I grew up with PLCs. Below that, we have, sensors and stuff in the process itself. And then we have a control area, if you will, at layer 2. And then layer 3 is my supervisory layer where the SCADA systems are and stuff. And then we have this layer 3.5 we talk about, which is the white space in between the office space or the IT space and the OT space. And that's the layer where we build our demilitarized zone, right? And I have red firewalls installed above and below the DMZ. And the reason I do that is in drawings is because I really think you should have firewalls from different vendors with different chips and firmware in them, because there isn't a day that goes by that there isn't a vulnerability found in that technology. So it's reported constantly. It's mind-numbing when you start watching how many vulnerabilities are discovered. People are doing a good job of discovering them, trying to fix them, reporting, telling you that they need to be patched and upgraded and all that kind of stuff and what to do. But the reality is if you use two dissimilar firewalls, and I know your purchasing department's going to hate that because they always want to use the same thing, and now you got to have two spares, and it's a nightmare. But the reality is at least you have a chance that one of them will protect the OT space. In the DMZ, we run things like historians, and then up in the office space, people will come down and read the data out of the historians, and that's actually typically where we hook up remote access. So anyway, the problem is that, if we're going to hook up things like I/O, then not only is everything else in that stack because of routable protocols accessible, but now even the devices like my sensors, my inputs and my outputs could potentially be routable all the way to the internet and to remote workers. So something to think about. It's a big deal. We got to get good at this. So this is why the so what factor kicks in big time when we start talking about this. Now, I'm not suggesting we don't use this technology. What I am suggesting is that we learn how to use it very, very well. All right. So we used to, not too long ago, we got into this cycle of patching stuff once a week. Usually stuff was patched on Friday night. That gave IT a chance to fix it by Monday morning if something went wrong with the patch. Then we got smarter and we started patching on like mirrored demo systems. We got a different name for it. I forget what it is off the top of my head. But we would patch on these dummy systems, if you will, to make sure the patch worked okay, and then implement the patch on Friday night. And we learned all this stuff. It's what makes us hesitant sometimes. It makes us think through what we're doing, and we have to, because these are, whether you realize it or not, the entire computing infrastructure, the internet, all this stuff is very complex. It presents itself as very user-friendly, but the reality is it's extremely complex. If you ever look at a communication string, just going up and logging in your username and password to log into a website, you'd be amazed at the amount of traffic it takes to make that happen. So we've gotten to this point where patches are coming out all the time, and I don't know if you can see this. Let me highlight this. I'm recording this on the morning of January 19th, 2023, and I want you to see that patch came out on January 12th, 2023. So the reality is that we are in a situation where this is tough. These are, and this isn't vulnerabilities in anything. This is vulnerabilities in industrial control systems. So, and you could read down through there and you might say to yourself, well, none of those are mine. Jim, that doesn't really matter. These come out almost every day. So it is a big deal. And trying to keep track of this stuff could drive you crazy. So we've got to think this stuff through better and better and better. So the challenge we have is, how do I run a plant and do this? It's very frustrating. So let me just share some other things real quick. So this is really interesting. I apologize for the red mark that carries through when we do this, but Chemical Security has its own webpage up on this Cybersecurity and Infrastructure Security Agency that's run by the United States federal government. So you can go up to cisa.gov/chemical-security, and this will help you, quite frankly. I always hesitate to say that about the federal government, and I mean that jokingly to a certain extent, but it is fair to ask ourselves sometimes, but the federal government is trying to help. It can get in the way, it can create some goofy laws and stuff that make it difficult for us to do our job sometimes, but the reality is, especially in this area around chemical safety and chemical security, they're taking it very seriously. And this is perfect evidence, so I would recommend that you get familiar with this and use this more often. All right, so this is the second slide where I'm using unusual graphics. So in the earlier slide, the very first slide that was up in this presentation, there was a picture, a pencil sketch, if you will, of a chemical processing plant. This particular slide, neither one of these graphic images actually existed anywhere just a few days ago, and I did not draw them. That little color bar graphic that you see down here in the bottom right hand side, and let me just highlight it real quick. Hang on, I didn't actually grab the highlighter, I apologize. This little graphic down here in the corner. So that comes from a open AI engine called DALL-E, D-A-L-L-E. And what I did was I went up and I literally told the AI engine that I need a pencil drawing of a angry rabbit looking over a computer at me, and it drew this for me. It pulled references from lots and lots and lots of graphics around the world and pictures around the world of what these things look like potentially, and then it rendered this. It did the same thing with a chemical plant. I put in a long string of information describing what I wanted, and it built it. So the reason I bring that up is in the discussion when I did this live, people were asking questions like, well, why can't you just tell me where all the threat vectors are? Or why can't you just give me a list of things to do? And the problem is that every facility we go into is different, right? The process is different. The process is unique. If it isn't unique, if you bought your process from UOP like a lot of people do, and you're operating your process, and there are other people who make processes, obviously, but that one just rings in my head because I used to work for Honeywell. So you bought your process from UOP. It's a standard process, right? Controllers and everything are pretty common. And if you had 2 or 3 of those, you could assume that they're relatively the same. However, when you actually get into them, what you find out is the way they're connected, the way they talk. There are some nuances to them, and then the way you connect them, and the vendors, the integrators, that work on the system, the way they connect to them and stuff, that all changes a little bit from site to site and process to process. So the reality is that things are changing rapidly, And the reason I used the AI graphics in here is because I wanted you to understand just how advanced AI is getting. I went up and wrote in, I basically asked an AI engine to write a thesis for me, and I gave it some information, and it wrote a thesis based off of about 2 sentences of information. That's amazing, scary. I'll take it to another level. I went back to the same AI engine and said, could you write some Python code for me that does this? And it wrote Python code. And I went and ran the Python code on a test computer and went, wow, it actually worked. Now, Microsoft leaked out just this last weekend. I don't know if it was intentional or unintentional, but Microsoft has an AI system that can listen to just a few words. I have said way more in this presentation than it needs. And it can take those words, the timbre of my voice, the pattern to my speech structure, the way I pronounce words and stuff, and can make some decisions and literally write a speech that sounds like me talking. Now, why am I sharing this with you? Because your boss is going to look at you just like that and say, you've got this under control. And your answer is probably going to be something like, sure, or maybe. Honestly, after you've watched this presentation, it ought to be maybe. If I got asked the question, I'd say, I'm trying to, and I think I've got most things covered. But the reality is, and I'm a pretty good cybersecurity guy, the reality is my answer would still be maybe. And of course, knowing what the boss knows, he's going to say, well, let's get IT involved, right? And IT is going to come along and say, all right, so let's do a vulnerability assessment. So let's take a look at that. All right, so let me start off on this slide by saying it isn't my intention to insult anybody in any way, shape, or form during this presentation. I make light of interacting with different groups of people, the federal government, IT departments, management, stuff like that. Please don't take any of that wrong. It's designed to emphasize some of the weaknesses that we have when we deal with stuff. It's very easy to be told no and just accept it and walk away. The reality is, I'm going to ask you, when it comes to cybersecurity, to stop accepting no as no and start accepting no as maybe and try harder. So let's talk about IT's approach to a vulnerability assessment. So IT does magic stuff. That picture on the left-hand side, I really love it. It's, the switching architecture, the way we build routers today, firewalls, the way all of that is put together and works is, quite frankly, really fantastic. But the problem with a vulnerability assessment, especially when IT suggests doing it, is they're looking for weaknesses, things like open ports, missing patches, bad design, stuff. There's nothing wrong with that. But when they come in and they start saying, well, we're going to do a vulnerability assessment, we're going to scan your OT network for that kind of stuff, you're going to hesitate, and you should hesitate. Your plant runs stuff that may have been running for 30 plus years. You need to ask yourself some serious questions before you start sending signals down a wire to tell the controller to answer questions. Can it, right? And the reality is pretty much all the programmable logic controllers, programmable controllers, any kind of logic controller, any kind of building automation system, anything of that nature really isn't designed to respond to an IT query. So you got to be really careful. And the challenge we have is that the traditional vulnerability assessment, especially from an IT perspective, is really designed for the office. It's not designed for the OT space. So hesitation is a good idea. And I'll go into this more in future slides. So as I continue to hammer people, I apologize. Let's look at this vulnerability assessment and the way they assess risk. So I was just looking at a book this morning called Cybersecurity for Industrial Control Systems. It was written by Tyson Macaulay, I believe is how you pronounce his name, and my good friend Brian Singer. And it stays near me all the time because the book's titled Cybersecurity for Industrial Control Systems, SCADA, DCS, PLCs, HMI, and SIS systems. And it's a good book, right? I mean, it's a hard read. I'm not going to kid you. It's, complicated stuff, but it's a good book nonetheless. And they have all this section. There's like a whole chapter on risk analysis. The ISA 62443 standard, which is cybersecurity, and I said ISA, this also is the IEC standard. So the IEC is starting to adopt more and more of the ISA standards. The ISA standards bodies do a real good job of basically weeding out what the right things are to go into standards. So the process safety standard, which used to be the ISA 88 standard, became the IEC 61511 standard. So it went global. The ISA 99 standards body and the ISA 99 standard became the IEC 62443 standard, which is global now too. So but all of this stuff, including even the ISA 62443 standard, looks at risk as like threat times probability times consequence. Okay, that makes sense, right? And it makes really good sense. And it's really funny in a vulnerability assessment, the first thing they say is identify an asset. And I'm like, okay, so one of the questions I usually ask is, so what kind of asset am I looking for? What are we gonna identify? Are we identifying an HMI station, a SCADA station? Are we identifying the firewall in the 3.5 layer DMZ? Are we identifying a process? Are we going to look at a whole process and say that's an asset to my company, the ability to refine a product, the ability to turn a chemical from one thing, adding some other stuff to it and some energy to it into something else. So what is the asset? And then how do you find the threat? How do you find the probability of that happening? A consequence, we're really good in the process safety world of figuring out what the consequence is if something goes wrong. But this is challenging, right? So the vulnerability assessment can be a real struggle. And then you go into, well, identify the threat to employing that asset. Now, hang on. This is very much an IT thing. They're looking at a switch or a router, and they're thinking like that, right? So the problem with this methodology is this is more like a failure modes and effects analysis approach. Great tool for identifying flaws in a design, doesn't identify process hazard scenarios. And so there are some challenges in trying to apply these things, if you will, to the OT space. So the vulnerability assessment folks show up on site and they go, hey, we're going to take, here's how we're going to look at this thing. Well, let's step back for a second. In the office space, they protect information at rest and information in transit. So you can think about it like your laptop and you're sitting in a Starbucks coffee shop and you're going to jump on the Wi-Fi network with your laptop. So a couple questions you have to ask is, what do I have stored on my laptop that could be compromised by jumping on a public Wi-Fi network, especially in a coffee shop where they don't validate who comes in and leaves and logs in and everything else, right? So it's like airports, right? It's an airport, hey, we have free Wi-Fi at this airport. And I'm like, yeah, I'm not using it. But you got to ask yourself a couple questions. And so let's talk about what that looks like. So we're back to the Starbucks and we're sitting there and we got ourselves a cup of coffee and we're going to log in and check our email, right? So we open the computer up, we turn it on, we log into the Wi-Fi system, and we make a connection to a public network in a public space to get on the internet. So there's information on my computer, and I'm about to hit a website most likely, and I'm going to authenticate myself on the website and transfer information. This is why websites now have that HTTPS thing in front of them, which means secure. And what that does is that means the browser is making a secure connection to this connection because you most likely did not turn on a VPN, a virtual private network, to make the connection. And you don't have any protection in the public space that you're in. So we're going to create a tunnel for you from your computer to that website so that your information is protected in that tunnel from the browser to the website. Okay, that's kind of cool. That means the information in transit is protected. That doesn't mean your computer is necessarily protected, connected to the system. So that's why we install things like malware and antivirus software, and we do all these things. So we want to protect information at rest on the machine, and we want to protect information in transit. And that's how IT people look at this type of stuff. If you're doing web development, like in the cloud, this is definitely how you look at stuff. But in the plant, we protect the product we're making. We protect the process that makes that product. We protect the safety of people, the equipment, the environment, stuff like that. We protect the machines. So there's a disconnect between these two worlds that gets really frustrating sometimes, and I know you feel it. I know everybody in the operational technology space feels it from time to time. We would like to have more of IT's help, and IT should be helping, and you should have a relationship with IT. But the other question we have to ask ourselves is, IT looks at it all as basically one great big thing, and the reality is some parts of our process, you could literally have the so what question asked all the time. You could, so you look at this chemical process, maybe there's I had Dolly design this for me, but you look at the graphic here in the bottom right hand corner, in the middle of there is a very high pressure reactor, a reaction chamber, if you will. And that particular device is operating, making a product at very high pressure. And if it leaks, it's leaking a product that could ignite and cause up to a vapor cloud explosion, right? So, maybe there's some parts of the process we should protect more than others. And so those are challenges that we face. We may have a service level requirement. So for instance, if we're making a product in that particular process that's being fed across our fence line to another company, then they're going to do the rest of the work and sell it to end users of it or whatever. So we may have a service level requirement not to affect that process, not to shut it down. Maybe our MTR, mean time to repair, is way too large. So we need to think about that. Maybe we need to protect that differently because it takes... I went and saw a site a few years ago where they'd blown apart a very large piece of equipment, probably from a water hammer, and it ripped the piece of equipment apart. And they called the people they bought it from and said, "Hey, you got one on the shelf?" Funny, not on the shelf. Do you have one out back somewhere we could buy from you? And the reality is they don't. And so that company's going to have to try to find a way to schedule in building it, buy all the materials and get it built. And the reality is it's going to take 18 to 24 months to get that thing built. So the mean time to repair on some of this stuff is really long. So, and then of course you have the world that we live in. Okay, you could lose control of your credit card in the IT space. In our world, you could die. So let's take a different look at this thing. So I want to go to management, and I need to build a business case for doing the cybersecurity thing in the OT space. But if we can't analyze risk correctly, how do we even get started, right? I mean, is management even going to pay for the vulnerability assessment when we're not sure why we're doing it and what the benefit is and what the risk is that we're trying to take care of? And so you're sitting there and you're thinking to yourself, well, hang on a minute. We already measure risk in this industry, right? So remember, this is a chemical manufacturing presentation here. Refining, it fits a lot of things that are critical processes, if you will. And so we're sitting here and we're going, we already do process hazards analysis. We did a hazard years ago. Now we're doing HazOps every 5 years. We do layer protection analysis to determine how much risk reduction we need. We need to understand the process under control very well. We're required to do that as a result of regulation in the United States, OSHA 1910 laws. You must understand under what circumstances control can be lost, right? So we need to know the consequences, the causes, and the safeguards for every single scenario where we could lose control. Maybe, just maybe, we could look at that data and find a way to use that to make our argument, right? Interesting thought. So let's dive into that a little bit. All right, so we're going to dive into it with a real-world cybersecurity project. This was my project. I got set here for quite a while. I was there for many weeks. And there were other people who showed up later to help me. And when I got there, this was a giant refinery. They spoke a foreign language. I actually had to sit through a day-long class just to be able to wear my FR gear and my safety shoes and my hard hat and safety glasses and walk around the facility. I had to go through a safety course and pass it in a foreign language. That was a little challenging, to be honest with you, but I did pass the safety course. I did not speak that language, or could I read that language, but I was able to figure out enough about the language because it was a Latin-based language. I would have been really challenged if this would have been in Chinese or something, but it was luckily a Latin-based language, so I could figure out the questions. I was subcontracted to a conventional network consulting group, and they came at the problem with the knowledge that they had, right? And, no insult to them. This is just the way they look at stuff, and it's the way they're trained, and they're very good at what they do. And their risk analysis calculations, like I pointed out earlier, were all based on assets, IT assets primarily. Or information. And it was like, no, that just doesn't really apply out here in the plant. The process hazards analysis, which was kind of like a hazard, was dated 1964. And I'm like, well, you probably have been doing these every 5 years since then, right? And they were like, no, this is the one we did in 1964. And I went, ooh, wow, this is going to be much harder than I thought. And we didn't know what a security PHA review was at the time, right? The security PHA review was created as a result of this effort, quite frankly. So I had to go in and figure a bunch of stuff out. So let me walk through what I went through. So the first thing I had to do is I had to identify the extent of all the process areas. I had to find all the equipment. I had to determine what process all that equipment was part of. And then try to determine how it was all connected together, not only from a piping perspective, but from a communications network perspective too. So I'm just showing refining here. This was part of the process, that they had on site, one of the processes, if you will, that they had on site. So you get an idea of how complicated this project was. So then I had to start trying to figure out what the network was. And strangely enough, the IT people were really not very helpful here, which was unfortunate. I really wish they'd have had some whiz-bang magic solution that could have come back and told me everything. But I had to determine the extent of the communications network too. And then I had to determine what was connected to it, how it was segmented, who controlled it, how it was configured. Where it was cross-connected and everything else. And it was a big monster beast, not unlike what you see here. This is a dumbed-down, simplified drawing that would fit in a PowerPoint. But basically, I had to figure this out for not only the people I was subcontracted to, but the particular refinery owners too. But because I was a ISA 62443 guy, I had read the whole standard, taken notes on it, written my own thoughts about it. It really made a very diligent effort to become really good at doing an ISA 62443 based or IEC 62443 based cybersecurity assessment. And so out of that, I determined that I had to basically, once I understood all these different areas, I also had to come up with basically what their network configuration looked like, what the zones and conduits would be if there really were zones and conduits, and then what they ought to be. I did a hazard type overview risk assessment of each process area. I created a list of vulnerabilities and ranked them. I established an existing zone and conduit model. So I did a good job. The customer was happy with the work. They paid our bill without any question. But the reality is, I didn't do a good enough job. I would have really liked to have done a better job. I would have liked to have left the customer with something other than a vulnerability assessment, but a true status of where they were really vulnerable to things going boom. So as a result of that effort and my frustration, The president of Connexus and I, Ed Marzell and myself, we talked on the phone a lot during this process. I wasn't frustrated, but I was struggling to find a way to actually do a better job for the customer other than just doing an IT type vulnerability assessment. I knew that there was equipment on the site that could kill me in under a minute, not just from the explosion, but from the gas being released. So it was like, look, this is a big deal, and they deserve better than this. I did what I was contracted to do. I did a good job. But the reality is I wasn't satisfied with it. And so Ed and I continued to talk and work this through, and Ed came up with the idea of how to actually, and let me explain. Ed actually teaches ISA process safety courses. He has an incredible mind and knowledge about this and the mathematics of risk analysis. And so he's teaching these ISA classes for process safety, and he lives in this stuff every day. Our company actually does this work every single day. And so between the two of us, we managed to wrangle out this process and wrangle out this book. And then going through a few editors at the ISA and going through peer review, which was a little painful, to be honest with you. We basically came up with what's called a security PHA review. And I got to tell you, this thing's tested, beat up, hammered, and the net result is it works. So it evaluates the cause and the safeguards and generates recommendations to minimize the vulnerabilities for safety functions, whether they reside in an SIS system, a PLC, or in some other kind of logic. We're going to do that for you. And we're going to, in this book, we'll actually teach you how to do it. In this presentation, I'm going to teach you how to do it too. So I'm going to stop calling it Security PHA Review because that's a mouthful. I'm going to call it SPUR for short. So a SPUR fits into existing project life and leverages your hazard analysis, the work you've already done. We're not going to ask you to do a ton of work. We're just going to ask you to sit down and review your HAZOP. You don't even have to look at the LOPA. Just review your HAZOP, all right? Pretty easy to do. Every 5 years when you do a HAZOP on a piece of equipment, schedule a month, a couple weeks later, or whatever is appropriate. Schedule some time to sit down and do a security PHA review of that HAZOP. I don't recommend that you do it at the same time, and I'll explain that better later. It complies with the ISA IEC 61511 process safety standard, and it applies to the ISA IEC 62443 cybersecurity standard for industrial control system. It provides also, it teaches you the right type of security choices for your design. Because they're all unique, right? They're all different. And IT shows up, they're looking at security as an IT guy. We're looking at security as process people. And so it really designs basically a way to make some really difficult discussions or decisions. It understands, it'll give you much better understanding of the possible attack vectors. So a question I got asked yesterday in the live session was, could you just give us a list of possible attack vectors? And I'm like, no, I can't, because it really depends on how you hook the thing up, right? Do you have a modem in that Hoffman enclosure out there that is connected to some vendor somewhere? That's an attack vector. Is it connected to the internet through two dissimilar firewalls, or is it connected through one firewall with a DMC created virtually in between? What firewall is it? Is that a potential attack vector? How about remote access for your employees? Is that an attack vector? Do you have stuff outside the fence line that connects back into your network? Do you have wireless signals escaping from your property? I don't know what your attack vectors are. There's all kinds of them. But this will actually help you identify your attack vectors. How could somebody get in to actually make the cause happen? Or how could somebody get in to override the safeguard? And then it'll actually help you understand how to assign a security level target when it's required. So security level target, if you're not familiar with it, comes from the ISA IEC 62443 standard. If for no other reason, if you buy the book, I'll actually explain security levels to you in exhausting detail in an addendum in the book, because the standard didn't do a very good job of it. So here it is. Security PHA review in a highly simplified form. Perform this, step one, perform this after a HAZOP, not during a HAZOP. If you do it during a HAZOP, it's going to confuse a bunch of people that are in the HAZOP. You don't need to confuse them. The small group of people that you assemble later to do this, the book will clearly identify who those people ought to be, but I'm just going to tell you, it's somebody maybe like me that's a controls guy and has enough cybersecurity knowledge and somebody who understands the process. If you don't have anybody who does all that in one, I suggest you at least have a couple people doing this. Most companies will have 3 people doing a security PHA review. They're going to have somebody who understands networking, computers, cybersecurity a little bit better. And then they're going to have somebody who understands control systems and somebody who understands the process itself. And so what you do is you basically say, is there a pathway to exploitation? The question you ask is, okay, we identified in the HAZOP a cause. So you look at the documentation for the cause and you ask yourself, could this be hacked? Well, how do you know that, right? How do you make that decision? Well, the answer is not too complicated, actually. Is it hooked up to a PLC? Is it hooked up to a programmable controller? Is it hooked up to an SIS system? Is it hooked up to, with a routable protocol, to a microprocessor? Does it have a microprocessor in it itself that could be jeopardized because of the routable protocol to it? Makes sense, right? Humanly operated things like valves, aren't necessarily hackable yet. And I say yet because that might change. What's happening is more and more we're using more and more virtual reality. And so if somebody goes out in the plant and they're going to watch somebody in a VR environment, maybe just a simple VR environment of a video on a cell phone, tell you how to actually operate the valve and what you need to check before you do. And could that be spoofed? Yeah, potentially. Absolutely. Someday in the future, it probably will be. So that's going to become a little bit more challenging as time goes on. Pressure relief valves, not really hackable, right? So when we look at, once we determine the cause is hackable, the next question we ask is, well, are all the safeguards hackable? And I do say all there in capital letters for a reason, because the reality is if any of your safeguards are simple mechanical devices like a pressure relief valve or a check valve, then they're really not hackable, are they? So if one of the things could prevent the cause, then maybe that's good enough. You may have to ask more questions, but let's just assume that all of the causes and the cause and all the safeguards are hackable. Then you're going to assign a security level based on the consequences of the scenario, and I'll explain that. Or you could propose a safeguard that's inherently safe against cybersecurity attack, and I'll explain that much more in the very near future. So before I get into I'll explain that more in the very near future stuff, let's have a brief commercial about a spur. So a spur is specifically designed to lower the risk to a tolerable level by lowering the likelihood of an occurrence of a consequence. That's it, right? We look at the HAZOP and we decide, is that a bad consequence? And if it is, could it be caused or could the prevention be defeated? And if the answer is yes, then you know exactly what you need to do to fix that problem. And I'll explain that, obviously, in great detail as we go on. Provides a better understanding of the attack vectors, makes the right choices for the design you have, increases efficiency by extending your risk studies that you've already done. You don't need to do them again. You don't have to hire somebody to do them for you. You did them already. It embraced RAGJEP. So it basically embraces the best of the best, right? And so, you can actually argue this with management. This is a good argument to have with management to say, look, we're going to do something specifically designed to look at the safety functions, the things that protect this facility from exploding or catching on fire or releasing a toxic gas or whatever it is. We're going to do something designed specifically to make that safer. So I'm going to call this table a lot of things during the presentation. I'll mix up the name a couple times. Please bear with me, but it's in essence what a lot of people call a corporate risk table. We've all seen it, the green light, yellow light, red light stuff, right? And if you got a red light, you got to move it into yellow. And if Depending upon how your company ranks yellow, you might have 2 different levels of yellow, so you might have to move it into the green, all that kind of stuff, right? So no magic there. It's all based on mathematics and the willingness to, the risk that a corporation is willing to accept. This is not your decision. Before you ever start a SPUR, this is an executive level decision that needs to be made. And the reason being is you're going to use that data to create a new column called the security level column. The security level column is going to decide for you, long before you start a SPUR, that if you accidentally kill somebody, and I'll highlight this, if your system could accidentally kill somebody, a single fatality, then the security level you need to implement is security level 2. You can't make that decision. That decision needs to be thought through and explained at this level up here, so that, because these things cost real money. Moving from security level 1 to security level 2 has a very real cost. And moving from security level 3 to 4 is almost impossible to actually do. So these things have very real consequences, and it needs to be, and this is honestly, this is a place where you could hire Connexus to actually help your company do this. We took a swag at this, which is what you see here. A strategic wild ass guess. So we just basically said, hey, what do we think these numbers ought to be? There's a risk to that, right? So your company might say, well, we're just going to use what's written in the book then. People do that all the time with standards. They say, well, let's just use what's written in the standard. Okay, that isn't necessarily wrong. And we designed that into these numbers with that in mind. But the reality is you really need to know what your own tolerance to risk is and whether that's acceptable or not. All right, so I like steps sometimes that are just listed numerically. And so I made an attempt to do that for you so that this would make more sense. So assuming you know how to do a HAZOP and a LOPA, you're going to assemble a modified team to review a HAZOP. And I already mentioned who that team might be. It's going to be somebody who understands the IT routing protocol stuff. It's going to be somebody who understands the control systems, how they're wired and connected, how they work, and it's going to be somebody who understands the process itself and how to keep it safe, all right, and how it's supposed to operate. So once you have that team together, then you can go in and instead of going node by node and doing a HAZOP and all that stuff, you just kind of go through the HAZOP and look at the things that you've decided need a safety function, all right? If it doesn't need a safety function, you already asked the so what question and you decided it wasn't important, right? That scenario isn't worth designing and spending a bunch of money to fix. It's just not that important. Move on to the next one. So you assemble your team. Another HAZOP's not required. Smaller team can do the job. Item number 3, identify scenarios where safeguards are vulnerable. Okay, I'm going to show you how to do that. I kind of already hinted at it. Then you're going to ask yourself, all right, is there a pathway subject to exploitation that would make those things that cause and those safeguards vulnerable? Then you get to ask the magic question, all right? So I call this the magic question because there is a so what factor here. It's interesting when you look at these things in review. You may look at the HAZOP and realize that somebody said, hey, you know, we ought to make this a SIL level 1. And then, okay, that's fair. What if it gets hacked? Could you cause it to happen? Would the safeguards kick in? Do I have enough safeguards? You got to ask yourself the so what question also in this effort, because the reality is it might not be worth doing, you know, the risk might not be bad enough to actually do other things. So that'll make more sense in a few minutes. Assign either a security level target. Remember that comes from the ISA/IEC 62443 process, or the Industrial Control System Cybersecurity Standard, or could you use an inherently safe solution to solve the problem? And then move on to the next scenario. So you're going to identify the things that you need to do, and then at some point you're going to sum all those up, and you're going to pick the most conservative one for a area, if you will, or a process, and then you're going to implement it. It'll make sense in the next slide. Welcome to the next slide. Okay, so this slide is the detailed version of a security PHA review. So let's start in the upper left-hand corner with start. Open the HAZOP report. Identify the scenario. Identify the cause of the scenario. Ask the question of the group. Is the cause hackable? You begin to understand how we've kind of written all your key phrases or keywords in here for you, but you can very easily start to think now through what those might look like. So you ask those questions and you go, okay, that's pretty cool. So now you get a yes or no at the hackable thing. And if the answer is no, there's no way to generate that cause remotely. That's actually a push button that starts a motor starter that isn't connected to anything because the push button uses a relay to actually put the power to the motor starter. So no, that can't be engaged remotely in any way, shape, or form. All right, document it, no concern, next scenario, cause can't be created. If the answer was yes, then you're going to take a different approach. You're going to identify the first safeguard. Is that safeguard hackable, yes or no? If the answer was no, then you document, no, not a problem, we got a safeguard. And remember, you're not trying to solve all the potential problems that could exist. You could have that safeguard and bypass, and the other safeguard might be hackable. So it requires a group of people to have some real intelligence and ask questions. But there is the possibility that if you have a safeguard and you're confident that that's good enough and it's not hackable, that your answer could be no, and you just basically document that this one isn't a concern and move on to the next one. If the answer is, yeah, that one's actually hackable, then you go on and say, are there any more? Identify and work through, okay, there are more safeguards, go through them all. Is it hackable, yes or no? And just keep doing that until you get to a point where you know whether you're protected or not. If you're not protected, then you're going to look at the consequence and you're going to ask yourself, is the consequence significant? Now this is the so what question, right? So if the answer is no, consequence isn't significant, then document it and move on. Documentation is really important here. If you don't document this, then if something does go wrong later, then you could be, found somewhat at fault for not having protected this correctly. If the consequence is significant, then you go on and you consider, well, can I add a non-hackable safeguard? So all my cause and all my safeguards are hackable. Rats. Well, before I go down the path of adding in a bunch of stuff for cybersecurity that might make the plant miserable, is there a way I could just simply change this? Maybe go in and create a couple of freeze blocks and put in the piping something else, like a check valve maybe. Something of that nature that would actually prevent this. And I'm just, hypothesizing on what it might be. It could be anything under the sun. But the reality is there may be a way to actually come up with a solution that doesn't require you to change the cybersecurity stance for this particular safety function. So something to think about. If that's true, it's feasible, then document it, move on. Obviously, you have to act on everything you documented, and we'll talk about that later. All right, so if it's not feasible, then you're going down a different path. And when you go down a different path, you're going to go over and you're going to say, okay, I have a hackable cause, and I have hackable safeguards. So now I need to take a look at this consequence or the corporate risk table. Remember I said I was going to call it different things. I apologize. The corporate risk table. When I look at the corporate risk table, I'm going to basically pick the security level based off what the HAZOP told me could be the consequence. I'm not reinventing the wheel here. The HAZOP says basically we could kill people. We could kill one person. If we can kill one person, back to process safety level 4. It's a category high. There's a single fatality. I need to implement security level 2. And you document it. And then you move on and do more scenarios. So pretty simple, actually, not too hard to do. After you've done just a couple of them, this starts to move pretty slowly. I'm only going to show you in this presentation to try to make this a reasonable webinar because I know watching a webinar for an hour is hard. is I'm only going to show you one way. And the reason I'm going to show you this way is because this is a no-cost way for you to do this. OpenPHA Desktop, you can go to Connexus.com and download OpenPHA Desktop for free. It's just free. It's period. It's free. It's PHA, HAZOP, and LOPA software. That doesn't cost you any money. The cloud version costs money. It's an annual subscription. It's very reasonable. It's probably the most cost-effective HAZOP and LOPA software in the world. To our knowledge, it is. But I want to show you that because we built this, we also built into it, whether you're using the desktop version or the cloud version, the ability to actually turn on functions. So you could turn on the cause as hackable, and then what that allows you to do is in the review process, you don't want this on during the HAZOP, but in the review process now, you actually have these little areas, these columns that show up, like the cause is hackable and the safeguard is hackable, and consequently the scenario is hackable. Now you don't have to answer the one I underlined. That one will be answered for you automatically based on the way you answered the causes and the safeguard question. All right, so this will keep track of that for you automatically, and then off to the right you can document everything that you decide in the meeting. So pretty cool solution. Let's move on. So I'm going to spend about 60 seconds on this slide. We already went through this. Key points just to review, and you can read it on your own time, but it basically, this is not a hard process. It's just not difficult. It's very easy to do. It doesn't take a ton of time. I encourage you to do it, and this just reiterates what I've already said. So here's where we pop into a real world scenario, right? So here we've got a process. We could have the P&ID node, this is basically the P&ID node right here. And, it's a drawing I actually created either in Adobe Illustrator or PowerPoint. I don't remember which one. I use both back and forth. Some things, quite frankly, are easier to create graphically in PowerPoint than they are in Illustrator and stuff. Illustrator, of course, is a much powerful tool. But this is a continuously stirred tank reactor. These things are really common. I actually, at one time, personally, was in a plant where I had put a variable speed drive in on the cooling water pump. And this plant was having trouble because the stupid pump kept shutting off every now and then, and they couldn't figure out why. And I'm standing in the plant, having been given a gas mask and all the other PPE equipment, including a detector for gas that I don't like at all. I remember earlier I said I used to work on a submarine. This particular facility had a gas that we were really scared of on the submarine because it was incredibly quick to kill. And so I had a little detector that told me whether or not I'd been exposed to it. And I say it that way because if that detector changed color, I was already dead. And I was smart enough to know that. Made me feel great. So I'm standing in the plant watching this thing run, and the lights dimmed. And I went, well, isn't that interesting? The lights and the next thing I know, I got tackled. I literally tackled like in a football game. I used to play football. And I got tackled, knocked to the ground. I'm laying on the ground. The next thing I know is there's a huge pressure change, and my ears are ringing, and the guy's yelling at me like, why didn't you dive when I told you to? And I'm like, okay, why did the lights dim? So anyway, the batch reactor, right? And I'm using a batch reactor in a chemical manufacturing presentation. I realized a lot of chemical manufacturing is continuous process, but it's also batch reacting. And honestly, batch reacting or batching is much easier for discrete manufacturing people to understand than continuous, right? So continuous is a little frustrating. The idea that you turn a process on and it runs for years and years and years without being turned off, and all you do is slightly, this is the way I ran a nuclear power plant, right? When we went to sea and I started up the nuclear power plant, the skipper of the boat expected the nuclear power plant to run until we came back to port. Continuous process that starts up and shuts down very rarely. Obviously, in emergency situations, you have other things you do. But batching is kind of a, okay, we're going to run this process for the next 26 minutes and then we'll start over again with another batch. That makes more sense, right? And it's easier to look at it and think about it that way. So a continuous stirred reactor, we're going to mix a reactant with another reactant. We're going to have cooling water running in the jacket because the reaction itself is basically generating a ton of energy in the form of heat. We do have a mixer typically in these that it's agitating the process and making sure the mixing is complete and the reaction is complete, and that the temperature is controlled. And if everything works great, we produce a new product that gets pumped downstream somehow. All right, so that's basically what this system does. If something goes wrong, that UZV 403 valve opens up automatically and dumps the reaction into a quench pit. And that's what happened at the facility I was at. And basically what I felt, which I thought was an explosion, was basically the water in that quench pit flashing to steam instantly, a lot of it. And so, interesting process. So let's break it and see what. So the cooling water fails is the cause in the HAZOP. So the reactor temperature increases, that's the deviation. The increased reaction rate escalates into a runaway reaction. Even if once it starts to escalate, even if you can restore cooling water, you probably can't overcome the reaction rate. In reality, most of these processes, you can't. So the automatic thing you do is dump quick. The runaway reaction, I just said that, but probably not. You're not going to save it, right? It causes a significant pressure increase as the product decomposes into gas and byproducts inside of the vessel. The pressure in the reactor vessel quickly rises in excess of the maximum allowable working pressure, causing the vessel to split apart. And then you have whatever that reaction is and those materials escaping into the environment, which could be bad. It could cause, in this case, a fire and potentially a vapor cloud explosion, depending upon when the gas ignites. So, bad consequence, right? And this is a very real-world reaction. So we pulled up the HAZOP, and it's open there. We have the PHA worksheet open for exercise number 4. By the way, this is actually in the book. This is a screenshot that I actually sent into the publisher, the ISA, for the book. And this is exercise number 4, the tank reactor runaway reaction. So the cooling water pump failed. Restarting it's probably not going to save it. A cyber attack could cause the pump to stop because it's hooked up to a PLC, or it could be potentially hooked up to a safety system too. Therefore, the initiating vent is determined to be hackable. So we answer this question, yes. Then we move on and we ask ourselves, okay, let's look at the safeguards. There's only one safeguard. It's hackable because it resides in a PLC or potentially a safety instrumented system. And so if the control system were taken over by an attacker, they could not only make it happen, shut the pump off, if you will, but the safeguard itself could actually be defeated or spoofed. So it is a hackable scenario. So let's look at recommendations then. So now we know we have a hackable scenario. We need to think about it. We want to do some things. So the first thing we think of is, well, wait a minute. That thermal well in the vessel actually has another temperature detector in it, and or we could just put in some. We could actually establish a security level and do that. All right. So we're going to write PHA recommendations and say we could potentially do either one of these. And we're already going into this thinking we need to do a cybersecurity thing, but we're going to go ahead and write in what the mechanical thing could be too, just in case we choose not to do the cybersecurity thing. So we need to pick a security level from the cybersecurity thing to write into that documentation, and so we're going to basically look at this and we go, okay, well in the HAZOP, it actually said that this could cause a potential single fatality because most of the time there's only a single worker there unless Jim McGlone is tagging along and wearing all his PPE gear and standing there looking up at the lights wondering why they dimmed, which would cause multiple fatalities because both of us were there, including not only the operator who knows what's going on, but the idiot who's staring at the lights. But most of the time it's only one person, so we're going to count that as a single fatality. That would be a security level 2. I'm emphasizing this a lot because you're going to find out that this is going to be a really common answer that, okay, we could kill somebody there. You may, honestly, just think about this for a minute. Maybe the safety function or the inherently safe solution here is to move the operator out of that area and not let them operate there. So the potential now for fatality, because you can't stay here more than this much time to set up the process, then you need to go over there behind the blow wall to run this process. So our chance for a fatality is pretty close to 0. Okay, that's a real solution to a problem, right? So you go to management, and that angry rabbit looks up over the laptop screen again at you and says, hang on a minute. Security level 2, what's the price? How long is this going to take? What's my impact to operations? And you tell him, and he looks at you and goes, hang on, we're not spending that much money to fix this problem. I realize that somebody could die, but the reality is there's got to be a better alternative. And you luckily recorded that there was this idea of doing a mimic circuit that was analog instead of digital and could potentially protect the process. So let's dive into that a little further and see what it was. So we take a look at it. We recommended a safeguard. And, this is an idea. So we're just going to look at this idea of doing a safety instrumented function in analog world. And I'm not recommending that we go back to analog for everything. I'm just saying that it's an option, right? It's a path that you could take. You might even decide that you want to put in a whole bunch of red emergency push buttons that open that valve up to dump the stuff into the quench tank, and that's your solution. Something to think about. Not automatic, but you're going to measure that risk because everywhere is different, right? Every process is different. Every process is a little different. Every chemical mixture is a little different, and every company has a little bit different risk profile. But we could put this, analog system in, and it looks like this might actually work. So it would work because there was a second thermocouple in that well. And we're going to take that second thermocouple and hook it up to a transmitter that generates a 4 to 20 milliamp signal that will vary. And once it reaches a set point, we're going to have a little bitty 4 to 20 milliamp signal monitoring and analog current monitor relay. And we're going to set it so that if it gets to a certain level, that it actually automatically sends the 24-volt signal to the solenoid valve and de-energizes the solenoid, venting the actuator and causing the dump to open. Cool. That would work. And it bypasses the safety system, whether it's running in a PLC or an SIS. Now, you got to take a look at this and ask yourself, is there anywhere here where I'm violating good process safety rules? And the answer is not really. There isn't. There's no real single point of failure here. You're not dual using stuff. You actually have a completely parallel circuit operating, releasing the pressure from that solenoid valve. Okay, so I screwed up the animation here, and the flow limiter showed up automatically in the bottom middle of this picture, and I'll explain it in just a second. But let's take a look at some non-hackable safeguard examples. So first one, pressure relief valve. Makes sense, right? It's spring-based. You just can't really beat these things, right? Rupture disc. Rupture disc work very, very well. Not a doggone thing wrong with them. The only thing wrong with a rupture disc is, unlike a pressure relief valve, it doesn't reset. Takes mechanical effort, takes some work, takes a work order, maybe a hot work permit, all that kind of stuff to go fix this thing. Some other cool things, a buckling pin. That's pretty cool. So a buckling pin works very similar to a rupture disc, just a different type. Kind of a combo between a rupture disc and a pressure relief valve. And then you have the picture to the right of the buckling pin, which is a flow limiter, right? So what that does is it's spring-loaded to allow a certain amount of flow through, and if the flow increases too much, the valve shuts. Or it could work the opposite way. If the flow is too low, the valve shuts. So I can't imagine a scenario where that would be appropriate, but it might be. All right, other ones. A check valve. I already mentioned this once, but man, a check valve is a very simple device, works very well, and could solve a problem. I deliberately put the word mechanical into this overspeed switch. The reason I did is because it's getting harder and harder to buy a mechanical overspeed switch. They all have remote connectivity now, and you can program them and change the set point. You can configure them and test them and do all this stuff remotely. So the question I have to ask is the hack to the uranium centrifuges in the mountain to equipment that wasn't connected to anything that technically didn't exist anywhere in the world and that nobody knew about it. Okay, that's not technically true because some guy named Ahmadinejad went through the facility and let photographers take pictures, which is how everybody else figured out how to attack it that did it, whoever they were. But the reality is they defeated the overspeed signal so that the centrifuge could be operated faster than it really should be. And the operator interface and the data historian said everything was fine. So it was a man-in-middle attack on a programmable digital overspeed switch. That could have been prevented if they would have just set it up and then disconnected it from the system instead of watching it. It would have tripped and alarmed separately. So you just got to think about stuff differently, right? It's unfortunate we have to do that, but we have to do that. And then current relays. So we just talked about a current relay, if you will, in a 420 milliamp current loop. Current relays are very valuable devices, and they could work. And I'm sure there are many, many more that you all can think of that I just don't have experience with. So in this class today, we described the problem and made a case for doing it differently. We described the security PHA review. We assumed that you know how to do a HAZOP, and like I said earlier, if you don't know how to do a HAZOP with LOPA, we'll gladly teach you. We'll even help you and lead you through them. Like I said, there are an army of people here that do that every day, all over the world. We showed you how to perform a security PHA review on a HAZOP, and then I took it to another level and did the batch reactor and showed you a real-world scenario and how to walk through the SPUR process to actually come up with a solution. And we briefly, in one slide, considered some non-hackable systems, and so we'll pop into conclusions next. So during the presentation, I actually mentioned OpenPHA Desktop, and I want to tell you how to get it, where to go get it. OpenPHA Desktop is on the Connexus.com website. It is free, and I'm not kidding you. There's no joke there. There's no advertisement in it that tells you how to upsell or to get, more features or anything else. It does most of what the cloud version does. The cloud version provides some really powerful stuff. If you go to the OpenPHA website, which is at connexus.com/software/OpenPHA, just remember connexus.com. You go there, there's a security tab. It's highlighted right here. A software tab. Click on the software tab, and you'll see a topic called HAZOP LOPA, and there might be something else in there, but click on that, and this page will open up. The cool thing is when you do that, then there's a button right here on the right-hand side that says download the trial and pricing information. When you click on that, it will move you nearer to the bottom of the page, and there's actually a link there that will take you to a form where you just register that you want the download, and we're going to ask you some questions about who you are, because If you call us and ask us questions, then we know what kind of experience you've had with it when you download it. If you have trouble in the future, we can send you an email and tell you that, hey, you need to, the software updates automatically, but you need to hook back up to the internet because you've been running your laptop remotely now for 9 months, and there have been 2 upgrades to the software. So we use it to keep track of who has it. We don't market to it. We don't sell you. We don't, as a matter of fact, pretty much no one's ever even going to send you an email. All that information is maintained in a website under my control, and it just doesn't get used for any reason other than just keeping track of who has it. But the desktop version is free. The cloud version, you can read about the cloud version. It'll tell you what the differences are. The cloud version is roughly about $1,000 a year to have access to. There are advantages to it, even though I would recommend that you work in the desktop version. Use the cloud version for the things it's designed to do to enhance it. Unless you're somewhere where you have really robust internet access, then the cloud version might be okay. But the reality is you're going to want to really work in desktop because it's not dependent on the cloud. And obviously they work together. You can upload and download to it, no problem. All right, so that's enough of a commercial about that. It is full-blown PHA software, and so HAZOP software and LOPA software, and it's got a lot of really cool features in it that I think you'll find beneficial. So I really thought about closing thoughts. I almost rewrote this deck. I actually originally created this closing thought slide quite a few years ago, pretty much right after the book Security PHA Review came out. I think the first company I presented this to was the Coke company out in the Midwest. But I read it, reread it, read it again, and went, you know what, I still agree with everything I wrote on this slide, so it didn't get changed at all, other than the graphic. The question I want you to ask yourself when you're thinking about this stuff is, does every single device need to be remotely controllable and programmable? I'm not telling you that there isn't value to that stuff. It's just, do you really have to have it connected? And I mean, I know it's going to be a nuisance to go out there, but what are the potential consequences of not taking the walk out into the plant and hooking up to it locally? And the potential consequences could be huge. So you got to think that stuff through. The microprocessor's awesome. Wired and wireless communications, off the charts. I mean, I use this stuff every day extensively. I'm not telling you that we shouldn't continue down this path. What I am saying is be smart about it. There are problems that can be created inadvertently. So consider that over speed switch again. Does it really need to have a routable protocol connected to it? Do you really need to plug that Cat5 cable in the drawing into it? Just think about that. It's something to think about. There are dry contacts probably in it. Maybe we could just use the dry contacts to tell us when something's wrong. All right, last slide. It's me again. I really got to go get another picture taken. I got that picture taken about 8 years ago, and first of all, I weigh a little bit less. Actually, I weigh quite a bit less, and I've aged a bit in 8 years. But that's how to get a hold of me, who I am. That phone number does ring through to my cell phone through Microsoft Teams. I might answer it on my computer if I'm sitting at a computer. And that is my corporate email address. I hope you've enjoyed this presentation. I am an employee of Connexus, and Connexus is a process safety company that is working very hard to basically make the art of keeping stuff safe more and more of a science and more deliberate at every step of the way. If you like this presentation, you want more information, I would recommend getting the book first of all. You can buy the book on Amazon.com. Probably easier to buy the book from the ISA though, and I think it might be less money. I think somebody's bought a case and put them up for sale on Amazon. We didn't put them up there. But the ISA sells the book. If you're an ISA member, I think you get a discount on it. The book's good. If you need help with any of the aspects of this, if you want us to help facilitate your very first Security PHA review, by all means, contact us. There is a contact form on the Connexus.com website under the About page, or pretty much under any service or product page. not on the main page, but if you go to the About page, there is a Contact Me form, and you can fill that out. What else? Yeah, so if you want us to help with your first one, if you want us to help with that discussion that needs to happen with the executive team about picking security levels, we'll gladly do that too. We'll do it for our standard hourly rate. We don't crank stuff up or anything like that. We just estimate the amount of hours it's going to take to do the job, and that's what we charge. All right, so this has been almost 100 minutes long. I apologize for that, but I think it was worth the time. And if you appreciate it, let me know. I wouldn't mind knowing that you got something out of it. Take care, guys. Have a great day. Keep it safe out there. Bye.